In this work, we study the feature reconstruction problem, where the input is the feature representation, extracted from a given black box face matcher, and the output is a subject's appearance. This task is quite challenging as the accessible information is very limited. Moreover, the feature representation is usually at high abstract level and difficult to interpret. There are some previous approaches that have partially addressed this task. For example, adversarial approach analyzes the gradients obtained from the black box classifier's outputs for the synthesis. However, they can only generate perturbations and support closed-set synthesis. Another direction is unrestricted synthesis approach, where full images can be generated given their high-level representations. Although they can provide the support for open-set synthesis, these methods require to have the classifier structure accessible. Recently, NBNet is introduced and support the synthesis from a black box classifier. However, with only pixel and perceptual losses, there are limitations of ID preservation when synthesizing different features of the same subject. We further address these issues with Bijective Metric Learning and Distillation Knowledge for the reconstruction task. In order to synthesize the subject face from his or her feature, a straightforward approach is to learn a generator structure to synthesize the face from the input feature representation. Then some metrics such as pixel loss, perceptual loss, or ID preservation loss are applied for the learning process. However, while the direct metric as pixel loss maintains low reconstructed quality, the classification-based metrics also meet many limitations, as the accessibility to the matcher structure for information backprop is not available. We introduce a new form of metric learning, namely bijective metric, which is a direct metric for image reconstruction, one-to-one mapping from image space to latent space, and the distance between latent variables are equivalent to that of images in image space. As two different images cannot be mapped to the same latent features, the metric learning process is more reliable than other classification-based metrics. In order to obtain the one-to-one mapping property, we firstly define a bijection that maps each image X to a latent variable Z. This bijective function consists of several mapping units that has special properties, invertible and attractable Jacobian matrix. With this specific form, the bijection can be efficiently optimized via log likelihood loss function. By setting the density function of latent variable Z as Gaussian, distance between images are equivalent to the distance between their latent variables, and efficiently computed a squared Wasserstein coupling distance between two Gaussian distributions. There are two other types of knowledge can be exploited for the synthesis task: the knowledge from the black box matcher, and the knowledge from real face structure. For the first type of knowledge, we exploit the angular information from the features extracted by the black box matcher. This information is used to train a student face matcher to mimic the behavior of the black box one. Then, with the knowledge about the embedding process learned by the student matcher, more guidance signal, such as the gradient or intermediate representation, is further provided to guide the synthesis process. The DiBiGAN is designed as a feature-conditional structure that takes two inputs, the feature representation and a background modeling variable. Then, the progressive growing training strategy is adopted to gradually increasing their levels of details for synthesized faces. The ID information is also injected to our reconstruction scales as a further guidance signal. All the distillation knowledge, together with bijective metrics, are employed to learn the DiBiGAN. We also put more weights on the distillation loss at lower scales, as it gives more control on the ID in the early stages, and laterally emphasize on other losses to enhance details in higher scales. The proposed DiBiGAN is validated on several testing subjects that haven't been seen during training stage. With white box setting, DiBiGAN is able to synthesize realistic faces with similar ID features as the real faces. When the matcher is set to black box mode, DiBiGAN has further shown its advantages, as it robustly produces plausible synthesized faces against in the wild facial variations, expressions, and occlusions. Moreover, by fixing the input feature and varying the background variable, different conditions of the face can be also synthesized. Further results can be found in the paper and supplementary. Thanks for watching.